To solve this rational equation, the first thing we must do is find the least common denominator. So here we have denominators of x and 3 on the left side and x on the right side. So our least common denominator is 3x because it's going to be the product of the two denominators we have. So now to solve, let's multiply each term by 3x. I'm going to multiply 3x, 3x, and 3x. So 2x over 3, I see that x and x cancel. So I'm left with 3 times 2, which is 6, plus, in the second term on the left side, I see that 3 and 3 cancel. So we have 5x remaining. 5 times x is 5x. And finally, on the right side of the equation, we have x and x cancel. So we have 7 times 3, which is 21 remaining. Now we can solve for x. So first I'm going to get all of my x terms on the same side. So I have 5x on the left. So let's move that 6 to the right. So I'm going to subtract 6 from both sides of the equal sign. 6 minus 6 cancels, so I have 5x remaining equals, and 21 minus 6 is 15. Now inverse operations one more time. The inverse of 5 times x is divide, so I'm going to divide both sides by 5. So I have x equals 3. And we want to check our answer. So first, I see that we have x equals negative 3. So if I can put that negative 3 doesn't make any of my denominators 0. So that's good. That means that it could be an answer. So let's check. Check. So I'm going to say 2 over 3 plus 5 over 3. Does that equal 7 over 3? Well, here we have like denominators. So to add the fractions, we're going to add the numerators. So 2 plus 5 is 7. Equals 7 over 3. That is a true statement. So x equals 3 is our solution. Domain and range of rational functions. Let's start with the parent function f of x is equal to 1 over x. If you'll recall, the parent function when graphed, because it's sometimes helpful to have a picture, looks like this. And we also had asymptotes. Remember, asymptotes are where the graph gets very, very close, but never touches, never crosses. So let's start with those domain values. Your domain are all of the values that make this function true on the graph for the x values. So if we look at our x-axis in the negative infinity direction, we have values, and the graph gets closer and closer and closer and approaches 0. And then the same is true for the right side, and then it goes to infinity. So we say that our domain, let's make that pen a bit smaller. For this function will be negative infinity to 0. And that 0 is not included because this graph never touches 0 on the x-axis. And we have a jump or 0 to positive infinity. The same can be said for our range. Remember range, I'll do range in a different color. Remember, your range are all of your y values. So range is going to be also negative infinity to 0, not included. We have that jump at 0 to positive infinity. So let's try another function. Let's do, remember from earlier this year we talked about the generic function of a rational equation. So we've got a over x minus h plus k. And remember that h is what's going to shift your function left and right. K is what's going to shift your function up and down. So let's do another example. Let's see, I'll call this one g of x is equal to 3 over x minus 2. So first let's look at our domain. Remember our domain? Domain is where is this function going to be undefined? So if I look at the denominator here, what makes this 0? Well, when x is 0, our function is 0. So I can say my domain in interval notation is going to go from negative infinity to 0 or 0 to positive infinity. My range, and this is where that function, where does it shift up or down? Here I can see this function shifted down 2 units because we have that minus 2. So here at the parent function, everything was here at 0, so if I shift down 2 units, my range is going to change to have a jump at negative 2. So we can say our range is from negative infinity to negative 2 or negative 2 to infinity.